If you've ever interviewed for a software engineering role, you've probably been asked, what happens when you type google.com into a browser and press enter? Most developers give the standard textbook answer. Your browser looks up the IP via DNS, opens a TCP connection, sends an HTTP GET request, and renders the HTML. While that answer might pass a junior interview, it completely ignores the complex systems engineering happening under the hood. In reality, within less than 100 milliseconds, your operating system kernel, network interface card, BGP routers, TLS cryptographic primitives, and global edge networks execute a synchronized choreography involving dozens of low-level protocols. Welcome back to Behind the Abstraction. Today, we're upgrading the classic interview question to the Senior Engineer Edition. Let's strip away the browser magic and trace every single packet from your keyboard to Google's data centers. Stopwatch Chapter 1, Hardware Interrupts and OS Kernel Space. It all starts at the physical layer. The moment your finger depresses the Enter key, a circuit on your keyboard closes, sending an electrical signal to your computer's interrupt controller. The CPU pauses its current execution context and fires a hardware interrupt. The OS kernel catches this via an interrupt service routine, ISR, translating the raw hardware keycode into a readable character event. The browser process, running in user space, receives this input event. Chrome's UI thread checks the address bar. Is google.com a search query or a domain? Because it contains a top-level domain, .com, Chrome recognizes it as a URL. If you have HSTS, HTTP strict transport security, preloaded in your browser binary, Chrome immediately transforms https://google.com before a single network packet is even created, preventing plaintext downgrade attacks right at the starting line. Stopwatch Chapter 2, the Deep Dive DNS Resolution Chain. Before your computer can send data, it needs an IP address. But DNS resolution isn't just one API call, it's a multi-tiered fallback hierarchy. Browser cache, Chrome checks its internal socket pool and DNS cache.os cache and hosts file. If missed, Chrome executes a system call, getadrinfo on Linux, macOS, to query the OS DNS cache and check etc. hosts recursive resolver. If still not found, the OS network stack constructs a UDP packet over port 53 and sends it to your configured resolver, like your ISP router or 8.8.8.8. If the resolver doesn't have the IP cached, it performs a full iterative traversal. It queries the root name server, which points to the TLD server, .com. It queries the .com TLD server, which returns the IP of Google's authoritative name server. Finally, Google's name server returns an A record for IPv4 or AAA record for IPv6, along with an Anycast IP address. Stopwatch Chapter 3, Packet Assembly and MAC Address Resolution. Now that your OS has Google's IP address, it opens a network socket using the socket system call. But your computer doesn't know how to physically transmit packets to an IP address across the internet. It can only transmit frames to a physical MAC address on your local network. This is where the ARP protocol, Address Resolution Protocol, comes in. If your computer doesn't have your local Wi-Fi router's MAC address cached, it broadcasts an ARP request across the local network, who has IP 192.168.1.1. The router replies with its physical hardware MAC address. Now, your OS network stack encapsulates the payload like Russian nesting dolls. Transport layer adds a TCP header specifying source and destination ports, port for 43 for HTTPS. Network layer encapsulates the TCP segment in an IP packet with source and destination IP addresses. Link layer wraps the IP packet inside an Ethernet frame containing your router's destination MAC address. The frame is converted into radio waves via Wi-Fi or light pulses over fiber, leaving your machine. Stopwatch Chapter 4, BGP Routing, TCP Handshake and TLS 1.3. Your packet travels across the global internet infrastructure using BGP, Border Gateway Protocol. Because Google uses Anycast routing, the internet routes your request to the geographically closest Google Edge point of presence, POP, rather than a distant central data center. Once the packet arrives at Google's Edge router, the two machines must establish a connection, TCP three-way handshake. Your client sends a SYN, Google replies with SYN ACK, and your client returns an ACK. Connection established.tls 1.3 encryption handshake. Because it's HTTPS, we need encryption. In modern TLS 1.3, this takes just one single round trip, 1 RTT. Your browser sends a client hello containing supported cryptographic cipher suites and a key share. Google responds with server hello, its digital certificate, and its public key share using elliptic curve Diffie-Hellman, ECDHE. Both sides independently calculate a shared symmetric encryption key. From this millisecond onward, all traffic is encrypted end-to-end. Stopwatch Chapter 5 Edge Reverse Proxies and Browser Rendering. Your browser sends an encrypted HTTP2 or HTTP3 QUIC over UDP. GetRequest.it hits a GFE, Google front-end, reverse proxy server. The GFE terminates the TLS connection, checks its edge cache, or routes the request through Google's internal high-speed fiber network to a back-end rendering service. Google returns an HTTP 200 OK response along with the HTML payload, compressed via Brotli or Zipper. Now, the browser's engine, like blinking Chrome, takes over the critical rendering path. HTML parser parses raw bytes into the DOM document object model. Tree.preloader scans ahead to fetch external CSS, JavaScript, and images in. Parallel.cssOM and renderTree parses CSS to build the CSSOM, combining it with the DOM to construct the renderTree layout, and Paint calculates exact pixel coordinates for every element, layout, and rasterizes them onto GPU layers. Paint. Within less than 1/10 of a second, the Google search bar appears on your screen. Stopwatch Chapter 6 Conclusion and Senior Mindset. From an electrical signal on a keyboard to OS system calls, BGP packet routing, Diffie-Hellman cryptography, and GPU rasterization, typing a single URL triggers one of the most sophisticated engineering achievements in human history. Understanding these layers isn't just about acing system design interviews. It's what helps you debug production latency bottlenecks, optimize critical rendering paths, and build resilient, distributed architectures. If you enjoyed peeling back the layers of this system abstraction, smash the like button and subscribe to the channel. Drop a comment below. What technical topic should we dismantle next? Thanks for watching, and I'll see you in the next one.